Today, I'm going to connect every atom in your body to a star that exploded. I'm going to take you on a 14 billion year journey from the Big Bang all the way to where you are now. We're going to trace every element in your body to a star. We're going to find hydrogen, the most simple, most basic, most elegant atom, the easiest element to understand. We're going to fuse it in the belly of stars to find heavier elements. And then we're going to watch the death of stars and how a gravitational collapse can create every heavier element heavier than iron. It all starts at the Big Bang 14 billion years ago. Science has no say on what happens at time equals 0, but where we can start is at time equals 0 to negative 46th power. At this point, there are no photons because the universe is much too hot to even sustain light. From here, all of the basic forces are all one. They all are one super force. Basically, gravity, which the stronger the mass, the stronger the force of attraction. And the strong force, which is responsible for keeping the protons and neutrons bound together in the nucleus of elements. The weak force, which is responsible for decay of atoms. Basically, the heavier the atom, the shorter its half-life, which means that the element's going to break down and shed some of its elements and become a new element. And then we have electromagnetism, which is a force that is mediated by electrons. The electrons are bound and it brings elements together. It's not in the nucleus, it's in the outer shell of elements. So where we start is at quarks. Quarks are what make up protons and neutrons. There's 3 generations of quarks. The first generation is the up and the down quark. These are what make up protons and neutrons. So inside of protons and neutrons, we have these quarks, which come in different colors. They exchange colors, and this is what kind of keeps them all together. This is the proton, and it's made up of 2 up quarks and 1 down quark. The charges are positive 2/3 for the up quark and negative 1/3 for the down quark. When you add the 2 up quarks and the 1 down quark, you get a positive 1 charge. And that's where the proton gets its positivity from. The neutron, on the other hand, has a different arrangement of the up and down quark. Basically, it has 1 up quark, which is positive 2/3, and 2 down quarks, which are negative 1/3. When you add the 2 negative 1/3 with the positive 2/3, you get 0. And that's where the neutron's neutral, no charge. From here, we're able to see that the proton, which is the nucleus of a hydrogen atom, the first element that it's the most abundant, so it makes up more than 70% of the universe. Now, the universe was at a very hot state, and everything with the breakdown of all the forces, that all happens within the first second. And back at this point, the Big Bang, there were no photons because it was too hot, and that's why when we look back with a telescope into the stars, we can't see back to the Big Bang because the universe was too hot, and there was basically this cloud of plasma and ions that was just, it overpowered the photons and the light couldn't escape virtually. So it took 380,000 years for the first rays of light to leave the cosmic microwave background, which is a fancy name for that plasma that was holding in all of the photons. Back at this point, this is the earliest that we can see with telescopes. Everything before this is based off of mathematics, laws of physics, and we can just follow the laws of interaction of particles on a micro and macroscopic scale and able to find out what happened before the 380,000 years. But it wasn't until then when we started to see our first elements from a telescope scale. From here, it took an additional 200 million years before all of this hydrogen in our universe, which made up more than 70%, and the neutrons as well, which made up another 20%. Everything else that you ever heard about was, oh boy, it took a lot of time. And I'm sorry. So basically, yeah, in the beginning of the stars, the most known about star is our own sun. Basically, when you look up into the sky, everything that you see is going to be basically more suns. Stars and suns are basically synonymous. The only thing is, we have a different timeline for how massive a sun is, or a star. And what is happening inside of these stars is the hydrogen nuclei are coming together under great pressures. And the center of them, not the electrons, which are out on the outside of these nuclei, the inside, the nucleus, are actually coming together and they're fusing. The first fusion is with hydrogens, and we get our helium, which is obviously that nice stuff that makes your voice so high when you inhale it. But so right now, our sun is fusing hydrogens together. And when the two hydrogens fuse together to create a helium, like our sun, it's letting off all of this heat and energy that was once being held together by the two separate, but when they come together, they create more stability, and then the release of heat and energy comes out. And this is just a basic diagram of some hydrogens coming together to create some higher isotopes, which are basically more neutrons and protons of hydrogen. One is called deuterium. It's basically a heavier hydrogen. So here we have the timeline of stars, and when you're a really heavy star, basically you have to be the mass of 8 times our current sun and able to go down the road to become a black hole. But everything smaller is just going to become a red giant, which basically means that when all the hydrogen burns out, it's going to increase in size 200 times its volume. The sun, when it becomes its red giant phase, is going to actually envelop the first 30 stars in our solar system. If you didn't know, that's all the way up to Earth. And it's going to start burning, it's going to start fusing its heliums. It can't do this for very long because our sun is surprisingly actually very small compared to other stars in the universe. The heavier ones become black holes and neutron stars. Basically, when it becomes a black hole, all of this supermass it runs out of the energy, which is the nuclear fusion. And when it runs out of this energy, it's just going to just all collapse in on itself. Because what was holding, you have the attractive force of gravity, which is trying to pull it all together. And then you have the emission of heat and energy, which is the nuclear fusion. So that's creating these two forces that are in constant equilibrium. They're trying to create this stability. And when it runs out of the force that's making it explode, basically, the nuclear fusion with all the atoms in it fusing, we get the collapse into a black hole. But right here we have a more supermassive star than our sun. Our sun's only going to fuse up to helium, and then it's going to die. It's going to explode into a planetary nebula. But what we have here is, this all does not happen at the same time. It goes through stages. First it burns off the hydrogen layer, then it burns off the helium layer, the carbon, and it does this all the way up to iron. When it gets to iron, it becomes unstable and can no longer fuse iron together. Because the higher the nucleus, it's a heavier element, it can't fuse anymore. And at this point, iron, it explodes. And it turns into a nebula, a black hole if it's large enough, or they'll just become a dwarf star, which is just smaller. Basically, nothing's going to happen. It's just going to become cold. So every element on this periodic table is created from a supernova, which is when the star dies and explodes and emits all of this energy. And when it collapses in on itself, all of the nuclei come together and they fuse different elements. Only up to iron is what's made in the belly of a star. So basically every element in your body comes from a star. Thank you.